Hi, good morning. Today, I'm going to present our paper, Privacy Preserving Event-Based Transaction System in a Decentralized Environment. I'm Rabimba Karanjai. This work has been done in collaboration with uh, Dr. Lei Xu, Dr. Zhimin Gao, Dr. Lin Chen, Kaleem, and my advisor, Dr. Weidong Shi at University of Houston. So, what we're going to talk about in this paper is we present a design and implementation of a privacy preserving event based on unspent transaction output. The transaction system, unlike the existing approaches that often depend on smart contract, where digital assets are first locked in a vault and then released according to event triggers, the event-based transaction system encodes event outcomes as part of the UTXO nodes and safeguards the event privacy by shielding it with zero knowledge. Proof-based protocols, such that association between UTXO nodes and events are hidden from the validators. Without relying on triggering mechanism, the proposed transaction system separates event processing from the transaction processing, where confidential event-based UTXO nodes can be transferred freely with full privacy in an asynchronous manner, only with their asset values conditional to the linked event outcomes. So first, let's look at the problem statement. To enable private and transferable conditional coins based on events, the system needs to meet the following requirements. First, the privacy coins. For example, use of Zcash as a base model for our initial target. These are associated with event conditions. The conditional coins can be validated against event outcomes. However, the link between the conditional coins and the events, both for event definition and event outcomes, should be hidden from the validators. Second, the system should support complete transferability of the conditional coins, where a conditional coin, after its creation, can be transferred unfettered by its current owner using the default privacy coin transaction protocols, regardless if the event outcome has been declared or not. Event processing and transaction processing are decoupled. Event processing separates from the conditional coin transaction. Event processing includes registration of events, event outcomes, announcement, declaration, and updates to each part of the decoupled system are asynchronous from each other. Fourth, all coins in the system, regardless if they have sent event conditions attached or not, are indistinguishable. The system does not treat the privacy coins with the event condition differently from the coins without event condition. Transactions involving privacy coins with event conditions are indistinguishable from the transaction without event condition attached. So a little bit note that the native extension of Zcash nodes with event tags would not meet this requirement because nodes can be distinguished by the event tags. So here, as we can see in the figure, it provides an example of association between event definition, event outcome, announcement, and event-based UTXO nodes. It shows 9 UTXO nodes named from CC1 to CC9, as we can see here. And 4 transactions named TX1 to TX4. For each transaction, input nodes and output nodes are enclosed in a colored bounding boxes. The coins in front of the arrows are input coins, and the arrows point to our output coins. Each type of data has its own logical chain, the corresponding Merkle hash tree. All the event definitions and event outcome announcements are in public. They are validated before appended to the ledger. In this work, we assume that the event outcomes are declared by the same parties who register the events to the ledger, and this is verified through a secure digital signature scheme. Verification of the event outcome itself is a separate concern, which could be supported through various established approaches, such as Oracle Service Providers, Event Validators, or Zero Knowledge Proof-based claim verification scheme. We assume that event outcomes are verified as part of the event processing before they are appended to the shared ledger. All privacy coins in the system are conditional coins. In the example, we can observe that all the coins CC1 to CC9 are paired with an event definition. A privacy coin without a real condition is configured to use one of the default constant events as its condition. For instance, CC1. This way, all the transactions involving the conditional coins in the system follow identical validation steps for the zero-knowledge protocol when deciding whether the transaction should be accepted by the participating distributed ledger nodes. Whenever a coin with a default constant event at its condition is transferred or spent, the output coins may maintain the same constant event as conditions. To associate a privacy coin node with an event outcome, an input privacy coin with a satisfied event condition can be split into two output coins with outcome of a new event as a condition. The two output coins must have opposite events outcomes as their conditions, as illustrated by the two transactions we see in TX1 and TX3. Each output coin has the same total value as the input. The conditional coins can be transferred freely, as we can see by TX2. In TX2, conditional coin CC3 is split into two output coins, CC4 and CC5, which can be transferred to two different recipients of the same recipient. To remove the condition, the coin spent needs to show a matched event outcome. As we can see in TX3 and TX4, both transactions have matched event outcome. Validation is done using zero-knowledge proof without leaking any information of the associated event definition and event outcome. After the condition is removed, a conditional coin output can either have a different event condition attached or switch back to one of the default conditions as its default event condition. Under this framework, it is possible to support actually a complex event processing and event reasoning. A calculus system of events can be defined and new complex events can be created on the existing events. In addition, event processing can be augmented with smart contract to enable diverse means of validating event outcomes. So when we talk about implementation, in this experiment implementation, we used XJSNark. XJSNark is a tool that achieves program-to-circuit conversion, that is to compile a user-supplied program described in a Java-like source language into a compact circuit representation, which the Snark libraries, primarily the libsnark compatible libraries, can recognize. XJSNark implements several optimizations to improve efficiency of frequent operations and reduce default size. We extended the Zcash implementation in XJSNark according to the described design to support event and conditions, which includes key anonymity options. A proving system is used to generate a proof of each joint split transaction based on the extended data models with event condition and algorithm. XJSNark built on top of the libsnark. Note, we have to realize that in libsnark we need to generate a key pair PK and VK. For example, in a zero knowledge proving system, eventually a verifier jet needs the VK public inputs and the proof to verify a conditional coin transaction. The system implements three Merkle trees for the conditional coins, the event definitions, and the event outcomes, in addition to public input, output, and witnesses defined in Zcash. We made extensions for different settings. All the key parameters like Merkle tree height, timestamp, event ID, event outcome ID, all are 64-bit in size. In the beginning, the circuit verifies the validity of different transaction scenarios by checking both input and event conditions and the output event condition. For instance, a conditional coin can be transferred with the event condition kept intact. In case a new event condition is attached, the circuit verifies the event outcome announcement associated with the input coins and the event definitions of the output coins. In addition, the proved circuit verifies the conditions that are common for all transaction scenarios. For security analysis, since we actually extend the Zcash protocol, all the security guarantees that comes with Zcash are preserved here. So most of the security properties that are proven in Zcash design and related publication still hold for conditional coins. In case of conditional coin though, the transaction indistinguishability is prime. So in our system, an observer cannot determine an event outcome is based on a conditional event or without a conditional event. The zero-knowledge proof protocol verifies existence of claimed event definition and event outcome against those two Merkle tree roots. In the conditional coin transaction, the total input coin is not value is not divided using zero knowledge proof. The prover must show that the two output coins satisfy the constraint that they embed the opposite outcomes of the same event as conditions. Some of the applications of this system can be said that it can enable and facilitate a wide range of application, including but not limited to transferable conditional asset with valuation based on the event outcomes, bill of exchange based on digital assets, future contracts, prediction of market and use cases areas like logistic, financial technology, insurance, especially to enable secondary market, etc. In summary, we can say that this work develops a confidential blockchain and event-based transaction system with privacy protection, which utilizes zero-knowledge proof technology. Extending the Zcash data model and the conditional event-based transaction design, the transaction protocol design encodes events outcomes as part of the privacy-shielded UTXO nodes. A main advantage of such design is that without relying on any triggering mechanism, the system separates event processing from the transaction processing of the additional privacy UTXOs. The event-based UTXOs can be transferred freely with their values to be conditional to linked event outcomes. Event privacy is protected with a shielded transaction protocol design using zero-knowledge proof. The design protocols are implemented and tested using XChestnut. Now, if we want to actually delve deep into the more different models on what is going on for data models, for data model, the conditional privacy coin ledger, there is a distributed ledger which records a sequence of transactions in append-only mode. This ledger is implemented as a blockchain where transactions are recorded in each blockchain blocks. The ledger supports multiple types of transactions designed for event registration and declaration, as well as transferring to the conditional coins. These definitions are defined as events of tuples of attributes as we can see in the figure. For a registered event definition, its outcome will be declared with an event outcome transaction. Each outcome is announcement includes the attributes defined in the table. If we see here, the security parameter goes into the setup where it gets the proving key. The proving then it goes to the prover where the prover runs with the witness and the public input. Once it can prove the system, the proof goes to the verification system where with the help of the verifying key, it verifies if it is properly proved and then it goes for an accept or rejection of that data model. The protocol extends the design of zero-knowledge based privacy transaction system with Zcash as its baseline model. Privacy-oriented blockchains apply zero-knowledge proving system as the underlying building block to protect privacy. A zero-knowledge proving system defines the parameters and processes as we have seen. A zero-knowledge proving system needs to satisfy the following requirements: completeness, succinctness, and the proof of knowledge. For completeness for security parameter, an arithmetic circuit has to be convince the prover that it can convince the verifier with the probability 1 against negative. In succinctness, the honestly generated proof pi has to be run, and in proof of knowledge, if a verifier accepts the proof outcome by a bounded prover, then the prover knows a witness for a given statement. The main extensions here are related to the joint split transaction. Joint split is a new structure added to the Bitcoin transaction format. A joint split contains three essential fields: the number of coins entering the shielded pool, the number of coins exiting the shielded pool, and a field holding a zero-knowledge proof attesting to the legitimacy of the transaction. For our extension, the confidential event-based UTXO, joint split is extended to support associating a shielded UTXO node with an event outcome. To highlight the changes in algorithm 1, 2, 3, where we have the prover system, the data and the steps unique to a system. In the default settings, the shielded conditional coin transaction described earlier records are verified against the entire Merkle hash tree. This achieves maximum privacy at the cost of performance. Verification of a Merkle hash tree path from a leaf node to root node is extremely expensive using zero-knowledge proof. In case of Zcash, it supports both shielded and non-shielded transactions. For non-shielded transaction, no additional privacy protection is provided. Coins are transferred in very much the same way as Bitcoin transaction. For performance optimization though, a further optimization is to apply a k-anonymity where an accessed record can be hidden among k-1 randomly picked records, as we can see. In case of UTXOs, one can hide the UTXO that is to be spent among k randomly selected valid UTXOs recorded by a distributed ledger. The size of k can be predefined as a constant. Several deployed cryptocurrency systems apply k-anonymity. For instance, Monero and Zither both apply them. At high level, cryptocurrency mixers are also based on the principle of k-anonymity. For our system to use that, we need to change a little bit of how the proven system works. The experiments were conducted using an Intel Xeon computer that has 8 Xeon cores and 64 GB RAM and running on Ubuntu 18.04. In the default settings, as we can see, a single Merkle hash tree is applied respectively for the ledger of the conditional coin commitments. The event definitions, the event outcomes for each ledger and the corresponding Merkle tree covers the entire ledger with 64 levels as tree height. To determine the complexity size of the produced circuit was measured as well as the proving key, the verifying key. The total number of constraints is 117,81616 without optimization, and with optimization of XJSNAC it's 8792171. The degree of corresponding therapy, the size of the proof, the key, and the size of the verification key are as what we can see here. Comparing with the implementation of privacy coins without the event, the expansion of circuit size is primarily due to verification of additional Merkle hash paths. The circuit size is overwhelmingly dominated by the Merkle hash tree path verification. The proving circuit is used for verification of the Merkle tree hash. The proof size is in bits of 2294. It takes an average of 261 seconds to compute the proof, and the verification takes an average of 0.042 seconds. Due to circuit size increase, the proof generation time almost doubles on average. This settings is the support for k-anonymity. In case of k-anonymity, user's input coin is hidden among k coins. K-anonymity designs provide significant performance advantage, meanwhile offers acceptable privacy in practice. In our implementation, the system supports a set with a constant number of input. A secret Boolean factor is used to indicate which coins in the set are the ones that a user wants to spend in a transaction. The Boolean factor is used as witness when generating a transaction proof. Our experiment shows that proving circuit size is not much affected by the size of k. For instance, everything else kept same, changing k from 16 to 32 only adds around 249 constraints after optimization. For this reason, the rest of the experiments we fixed k to be 64. For future work, the currently demonstrated system has certain limitations that can be addressed. The event conditions are in the binary format, although complex events can be encoded using Boolean logic on top of binary event outcomes. How to support flexible and efficient expression of complex events without significant increase of proof circuit complexity remains a research topic. Moreover, the current implementation based on SDSNARK inherits all the limitations of LibSNARK, which is based on the ZK SNARK proving scheme provided by the Zcash, such as secure setup. Since our protocols are proving system agnostic, it is straightforward to adapt the transaction protocols to other zero-knowledge proving systems to eliminate this limitation, like bulletproof. In addition, further optimization of the proving system could be realized. For instance, using a dedicated zero-knowledge proof system scheme. To summarize, the future work can be a support of rich complex event processing such as event reasoning, proposition logic for conditional coin, and more efficient implementation of the proving circuit and experimenting with zero-knowledge proving systems like bulletproof. With that, I conclude the presentation. If you have any questions, I'm ready to take it. Thank you.